You're not going to want to miss this episode of the AI Show where we talk about medical imaging with Azure Machine Learning. Make sure you tune in. Hello and welcome to this episode of the AI Show where we're talking all about medical imaging with Azure Machine Learning. I've got two special guests with me. Why don't you introduce yourself? We'll start with you, Harmke.
Sure. Hello, my name is Harmke Alkemade, and I work as a cloud solution architect for AI and machine learning, supporting our enterprise customers with AI use cases on Azure.
Fantastic. Andreas.
Yeah, Andreas Kopp from Germany. I'm part of the same team, also cloud solution architect, working on AI use cases with our global enterprise customer with some specialization on medical imaging.
Fantastic. So people that actually solve real problems, not like me. What problem are we solving today? We'll go with you, Andreas.
Yeah, I think it's fair to say that there is a lot of societal benefits when it comes to applying AI in healthcare use cases, like early disease prevention, improving the productivity of physicians, and also making healthcare more accessible. On the other hand, if we look at real world adoption, it's still relatively low. There are technical challenges, there are privacy concerns, and there are also skills gaps. So what Harmke and I did, we created, based on our customer engagements, we created a couple of assets that data scientists working in healthcare settings or medical professionals can use to accelerate their use cases.
Fantastic. And this is all in the space of medical imaging. Can you give us an overview of what that actually means for those that are watching?
Yeah, if you look from a computer vision perspective, there are some considerations. I think the most obvious one is about responsible AI. We are talking about very sensitive patient data, personal data. Then there are also strict regulations, and you can also imagine if we use AI to assist diagnosis and medical decisions, there is also patient safety. So Microsoft provides a quite comprehensive framework, which ensures that you have all guidance and also techniques that you can ensure that those solutions are implemented in a responsible fashion. If we look at it from a technical point of view, there are some challenging, also very interesting features. So for example, images, microscopy images of tissue, for example, these are typically in the 80K, 90K pixels resolutions per dimension, so much higher than the capacity of typical computer vision networks. Then we have something which we call multi-view inference, for example. So a radiologist will typically use more than one X-ray to make a diagnosis. So we have to use special neural networks that do multi-view inference based on multiple images. And then often it's not images. So often we are talking about stacks of images. So 3D volumes can be hundreds of images. And sometimes we also have a time dimension. So it's like a 3D movie where you look at a beating heart, for example. So this is quite challenging from a computer vision perspective. Labeling can be very expensive in those settings. So think of a stack of 2D images of 300 images. So it can really take hours, sometimes even days to label, to annotate those data. And then sometimes we also have to be very careful about distractors, which are visual artifacts that might be correlated with a target label. To give you an example, imagine you have an X-ray of a patient laying down. These X-rays are typical of lower quality than standard X-rays. But the fact that the patient is lying down can also be correlated with a disease, right? Like pneumonia. And then instead of learning the real characteristics of the disease, maybe there's just a distractor that is picked up by the algorithm. So there is a risk of those artifacts. This is why explainability is key. So in order to make sure that the neural network is really learning the relevant features instead of picking up distractors. And it's also, of course, important for regulatory approval. And acceptance by the physicians themselves to make sense for them.
Yeah, so it looks like there's a lot of things that you need to take into account. It feels kind of fuzzy to me. Can you maybe tell us a specific example of where all these things come into play?
Yes, sure. So we would like to show a real-world demo, quite a challenging demo. So this is about biological cell segmentation. That's actually a pharmaceutical use case. So imagine you want to find out if a drug you are developing, if it is effective or not. You give the ingredients to cells, to biological cells, and then you do things like counting or measuring the size to find out if your drug is effective. Yeah, and in order to do that, so pharmaceutical customers are more and more leveraging machine learning to count those cells or to measure it. And what we have here is a very interesting real life data set. It's a large scale data set. It consists of 1.6 million cells, experts annotated. So there was a team of experts actually drawing polygons for 1.6 million cells. And what we are going to do in a minute, what Harmke is going to show in a minute, is how we can leverage Azure Machine Learning to classify, but also do segmentations for these kind of cell to support such use cases. And it's a very interesting use case because we are actually leveraging a new capability, which is called automated machine learning for images. So we have automated machine learning for tabular data for quite some time in Azure ML. Automated machine learning for images is relatively new. It's in a preview. It supports you for training, classification, object detection, and instance segmentation models. And the big benefit, in particular for a medical expert who's not a data scientist, is that while you need some training code to define your experiment, there is no need to do any custom coding for developing your model architecture or to provide custom training codes. So automated machine learning is taking care of that, and it also supports the hyperparameter optimization process by launching a couple of runs. And when the process is done, you simply choose the best model. You can deploy the best model or download it as a standard PyTorch model.
And that's interesting because we did a show on AutoML for images. Basically, if I remember correctly, and Andreas, you can correct me, AutoML for images finds the best configuration of parameters to do object detection, and you're pointing it at this cell problem. Am I getting this right?
Exactly, for instance segmentation. That's exactly the demo that Harmke is going to show now.
Fantastic. So Harmke, it's all up to you. Can you show us how you went about doing this?
Sure. What you're looking at right now is the demo that we have developed for cell segmentation. So we are using it directly from Azure Machine Learning as a notebook. And of course, the notebook starts with importing some of the necessary libraries. But directly after that, what we are doing is defining our experiment. And this is important because we will use Azure ML not only as a development experience to develop these notebooks and run the code in it, but we will also track all the important artifacts that we are created during the model training in our workspace. So that is really useful.
So if I not to interrupt you, but this is basically a notebook inside of Azure Machine Learning Studio, and this is a pre-formatted notebook that's everything's already been done. Is that right?
Yeah, indeed. So in this case, I already ran all the cells just before the demo, but we have the code available in GitHub, so everyone can try it themselves in their own environment, of course.
Awesome. I'm sorry to interrupt, but keep
No worries.
showing us this stuff.
Of course. So then we have the next step here, which is basically about defining the data set. So what we did before the demo as well is to upload both the images that we have, but also the files that contain the annotation to a blob storage account that is connected to our workspace. So using the path where this data can be found, we can define the data set that basically combines these images with their labels. And we had to do one step in between. That was to convert the labels into a format that is supported by AutoML for images. So by default, with the data set, there is a COCO format in which these annotations are delivered. But for AutoML for images, we needed a JSON lines format. So that's where we needed some custom coding here. But for now, we just defined our data set, and this is to make sure that we can actually use it in AutoML for images.
So this is the data part of making sure all the data is in the right format. Okay, cool.
Correct, yeah. And then the next step is to show what this data looks like. So we are creating a very small set of some sample images that we have in our notebook, just so we can show what this ground truth for these images look like. So these are the actual annotations that can be found in the data set. There's no model involved here yet. And this is, again, basically to show how challenging this data is for a machine learning problem. So if we look, for example, at this image, we can see that it's very low contrast, right? So for some of these cells, even with the naked eye, it's quite difficult to identify where these cells are on these images. And you also see how distinct all these different cell types are. So yeah, that makes it really a challenging data set to train a machine learning model on. But for us, that also makes it very interesting.
Yeah, I mean, this is really, really cool that you're seeing this, and it helps, set the ground truth to see the actual complexity of the problem. I really like this.
Yeah, definitely. So after reviewing the data, what we can do is to train our initial baseline model. So for our baseline model, we will just do one iteration of model training with some fixed parameters that we set. So we defined the model architecture here, for example, that we want to use, the size of the images that we will use for the training. And what we also define here is the maximum amount of detections that the model will do on every image. So by default, in AutoML for images, this is set to 100, which means that after the model is trained and it will detect the objects on these images, a maximum amount of 100 objects will be detected. But for these cells that we are using, this is not sufficient. So some of these images contain more than 3,000 cells. So that's why we had to increase this value to a little over 3,000.
I see. So the default is 100.
Yeah.
And you're like, nope, this is a more complicated problem. So, okay, cool.
Definitely. Yeah. So after setting these parameters, we will define our AutoML image config. So this basically sets all the configurations so we can do our baseline run. And then it's a matter of submitting our experiment to our workspace. And important to note is the reason that we're starting with a baseline run is because only the baseline run itself is already quite intensive. So we use quite heavy machines to execute this baseline run. But even with heavy GPU type of machines, it took more than 4 hours to train this model on this data, just with the fixed parameters, only one iteration. So it's quite an intense model.
And how many images were there, just to remind us all?
In total, there are 1.6 million cells annotated on these images.
And it's impressive that it can do that in 4 hours, just out of the box.
Yeah, and to be fair, we only used 50% of the data here. So we could even improve the model later on by using the full data set. But for now, 50% of the data was sufficient for the results that we wanted to achieve.
That's cool.
So after training the model, we can look at the experiment data that we have gained from it. So this is also where you can see, right, just the one run that we did that took almost 4.5 hours to complete. And we can see the performance that we achieved with it. So you see that the performance improves over time while the experiment is progressing. And at the end of the experiment, we achieved a mean average precision of 0.46. And this is actually quite a competitive result. If you compare it to the results from the paper that was released together with this data set, we were really impressed by the results that we got from this baseline run with AutoML for images.
Oh, that's not bad. So for those that don't know what mean average precision, what does that mean?
Yeah, it's basically an accuracy value that indicates not only if the segmentations that were created were in the right category, so we have to determine right which type of cells can be identified on these images, but also the exact location of the cells on the image itself. So it's basically a combination of the cell type and also the location of the cell on this image.
I see. So does that mean it was getting about half of them right, or is it more than that?
Yeah, it's a bit more complex, to be honest,
Got it.
because with a simple classification problem, that's basically how you could look at it. But in this case, it's looking at every cell. So it's mostly looking at the overlap between the actual the ground truth values and the segmentations that were predicted by the model.
And I guess the moral of the story is that it's already super competitive just by doing the basic AutoML stuff with
Yeah,
one choice of things to do. Is that right?
definitely. Yeah, yeah.
Cool.
So that's what we did here. And after doing this baseline run, what we focused on is a part where we are deploying the model. So we can actually create some predictions with it. So the first step in that is to register the model from our AutoML experiment to our workspace. That's what we're doing in this step. And after doing this registration, we're making the deployment. And this deployment will happen on a AKS cluster, so Azure Kubernetes services. So using this, we can create a real-time endpoint where we can then send images to, and we basically get the predictions in terms of which cells are located on the image according to the model. And for that, we not only need the model, but also a scoring script and some configuration. And we also get that directly from our AutoML run. So that
Hold
is
on. So
really easy.
this is the part that's interesting because I was like, oh no, now we got to write some code to look at all the bounding boxes and DROM and whatever. You're saying that the scoring script is generated by AutoML as well?
Yeah, yeah, this is really useful. Yeah, yeah.
That's cool. That's cool.
So that's what we're doing right here, right? So we are downloading these files from our experiment run from AutoML, so we can send them to our web service that we are creating. And that's the last step here, is to make the actual deployment. So here we say model.deploy with the configuration and with the scoring script that we all got from AutoML. So no custom code needed here. And then eventually we have here our endpoint that we can use to create to predict some segmentations on images.
That's cool. That's cool. So and now you're showing us how you actually use that endpoint now. Am I getting that right? Okay.
Yeah, that's correct. So here we are retrieving this endpoint, and what we are doing is that we send some images to this endpoint, and then what we get is some predictions in terms of where these cells are located on the image. And that's what we have visualized right here. So we are using the same sample test set that we used earlier, but now we not only have the original images and the ground truth segmentations, but also the predicted segmentations that are generated by the model.
And this is really cool because you only tried one thing, and in theory, AutoML for images should let you range across a whole variety of parameters to get even a better result. I
Yeah.
think, right?
Yeah, no, and that's completely true, and that's also what we have in the last part of this notebook. That's also where we showcase how to do this hyperparameter search, how to actually select the parameters that give the best performance for your specific experiment.
Oh my goodness! And were you did this find something that was even better than what you already had?
Yeah, we did find something that was even better. Yeah.
Oh my goodness! This is really cool. I like how there was a problem and then there was a solution. Usually with these kinds of things, we're talking about like a couple months of research to even figure out if something is feasible. It's cool that you're able to just literally try something and right away get some responses. Is this code available for folks to actually look at and use?
Yeah, definitely. So we have a GitHub repository published where we have 5 different examples available. So one of them is this LIVEcell notebook that we are currently showing.
Okay, so that's cool. You're mentioning other examples. Andreas, can you tell us a little bit about what those examples are?
Yeah, sure, I can do that. So here you see the overview of our repository. So as Harmke mentioned, so 5 of those are published. Yeah, and we look at it from 2 perspectives. So one is we have different medical use cases like brain tumor detection, like pneumonia detection, or this cell segmentation case that you've seen. But we also want to look at it from different perspectives when it comes to the AI approach, or let's say different personas in medical organizations. So for example, there is one demo where I'm a data scientist, so I'm really specialized on data science. I just want to use Azure Machine Learning and benefit from a collaborative environment and manage all my assets, but I want to use all the flexibility from using Python, PyTorch, and those libraries. But then maybe the next iteration to increase the maturity is to leverage machine learning operations, so to optimize, to automate the process. And then we also have these use cases where I'm a different persona, so I'm a medical expert, not a data scientist. I want to leverage automated machine learning for blood cell detection or cell segmentation, as we've seen. And then 2 more things which are extremely relevant for medical settings, which is protecting patients' privacy. So we are integrating differential privacy to protect the model, so it's not possible to extract any personal data from the trained model. And also we are currently working on a cross-organizational training between a couple of hospitals using federated learning, so which basically means they are combining they are training a combined model without needing to share any data for that.
This is really cool. It's been a pleasure. We're out of time. We should have you on again to show us some of these other ones. Thank you so much. Where can people go to find out more about these things?
Yeah, we have 2 links. One is the repo itself. You see the link here. And then also we have a nice background article on towards data science, where you can understand the whole background, even if you're not interested in the coding experience, so more a conceptual perspective.
Well, this has been amazing. Thank you so much for spending some time with us. We've been learning all about medical imaging with Azure Machine Learning, a really cool image segmentation problem with AutoML for images. Thank you so much for watching, and hopefully we'll see you next time. Take care.